Hello everyone, this is Ashwini from Cheenta.com. Today, I want to talk about this particular problem. One of the students at Cheenta actually posted this in one of our WhatsApp groups. I was having a lot of fun with this problem and I thought, why not share with everyone? Actually, there are two major strategies, problem-solving strategies, that are useful for mathematical Olympiads. We will apply them in this problem. So it's just not a solution video. I want to share with you these two major strategies that are used in a multitude of problems. It's also useful for ISI-CMI entrances if you are interested in that. So quickly, what the problem says is that we have a triangle ABC, any triangle, and we draw two Chevians. So maybe you have not heard of the word Chevian. Chevian is any line that connects a vertex to a point on the opposite sides in a triangle. So BQ is a Chevian, CP is a Chevian, and they meet at the point R. Okay. Now, we draw four perpendiculars. One is the perpendicular of the entire triangle, that's small edge. We join PQ and draw HX, which is the perpendicular to PQ. We draw this perpendicular HY and we draw this perpendicular HZ. And we want to prove that HX times HZ, HX times HZ is this one, the product of these two, is equal to the product of H times HY. That's the second piece. How do we go about it? Now, whenever you see product of some lengths, this is the first strategy. Let me write it down. This is the first strategy that usually works. You convert it into ratios. Instead of working with products, you convert it into ratios. So what I'm going to do is I'll just write it down. I will convert it into H by HZ equal to HX by HY. So the ratio of HX and HY, we would like to show that that's equal to H and HZ's ratio. That's the first strategy. Convert the product into ratio. The second thing, and probably more important, is that whenever you see ratio of lengths, in many of those situations, it helps to convert it into ratio of areas. So you go one dimension up. It's kind of counterintuitive. You were dealing with lengths. Now you are dealing with area. So you have gone one dimension up. But this is a surprising theme that is true in different parts of mathematics. Sometimes to understand lower dimensional stuff, you have to go one dimension up. I was talking about this integral called the Gaussian integral. One famous way of solving this Gaussian integral is to go one dimension up and then find the formula becomes very easily available. Maybe in some other video I'll talk about it more. This is also related to normal distributions if you are into probability theory. It's very exciting, but let's not worry too much about it. But just remember this much. In mathematics, you may have to go one dimension up to get things simpler. Okay? All right. So now, let's come back to this. So H over HZ, I'm going to write it as a ratio of areas. Okay, so H is the height of the main triangle. So triangle ABC is the main triangle. H is the height of that. The area of it is half H times BC. And triangle RBC, this one, let's write it down, RBC, the area is half HZ times BC. Again, height times base times half. So if I take the ratio of them, half cancels, BC cancels. So you see, H by HZ is simply the ratio of ABC by RBC. The big triangle divided by the small triangle, right? Similarly, HX by HY is the ratio of this triangle by this triangle. We'll see in a second. So triangle APQ is half HX times PQ, and triangle RPQ is half HY times PQ. So if you take the ratio of them, let's cancel this off, we get it's equal to HX by HY. So what did we do? We have successfully converted ratio of lengths into ratio of areas. So we wanted to show that this is true. Let me just paste it. Okay, so we wanted to show that this is true. Now we have successfully established that this is equal to triangle ABC by triangle RBC, and this is equal to triangle APQ by RPQ. So if we can show that these two are equal, of course we have not shown it, but if we can show that these two are equal, then we would be done, right? Okay, so how do we do this? Okay, so here comes the strategy 2.5. You have written down the area of the triangle in half base into height formula. Just write it in another way. Write it in another way. So triangle ABC, we will be using the sine rule. It's AB times AC times sine of the angle in between, half of that. So triangle ABC, okay, maybe I can get the picture one more time here, just for reference. Okay. Okay, so triangle ABC is half AB times AC times sine of angle A. So AB times AC times sine of angle A, half of times half. That's the trigonometric form of the area formula. And RBC is half RB times RC times sine of angle R. RB times RC times sine of angle R, right? Similarly, triangle APQ, this one, is half AP times AQ times sine of angle A. AP times AQ times sine of angle A, and divided by, well, this one is half RP times RQ times sine of angle R. Well, this one was R and this one is vertically opposite, so that's also R. RP times RQ times sine of angle R times half. So we want to know whether these two are equal. Of course, sine A by sine R is on both sides, so we can cancel them off. Half cancels off. So it is sufficient to show that AB times AC divided by RB times RC is equal to AP times AQ divided by RP times RQ. If we can show this, then we can just multiply both sides by half and sine A by sine R, and we can go back to the areas of the ratio of areas and go back to the ratio of heights. You see how it's going, right? We are sort of backtracking the entire thing. We want to see if this can be shown. Now comes the final thing. It's the Menelaus theorem. So if you know what the Menelaus theorem is, let me write it down. I'll remind you. So this is the Menelaus theorem. What it essentially says is that if you have a triangle, let's say X, Y, Z, and if you have let's extend one of the sides like this, and let's draw a transversal. Transversal is a line that cuts through the three sides of the triangle. So XY is one side, XZ is one side, and YZ, of course, it doesn't cut internally, it cuts externally. Let's suppose this is P, this is Q, this is R. Then the Menelaus theorem says is that you can start at any vertex, YP by PZ, YP by PZ times ZQ plus that by Q, QX. So ZQ by QX times XR by RY equals to 1. XR by RY. So notice what I just did. I started with a vertex. I just traveled around the entire triangle. That's how I at least remember this. So you take the product of these three things, it's 1. Actually, if you take the signed product, it will be -1. I'm not going to go into that detail. Just for magnitude wise, this is just 1. This is the Menelaus theorem. So we will be using the Menelaus theorem twice to actually get the final result. So what do we want? We want this. Okay, let's copy this and let's keep it in our radar. Let's paste it. And let's get the picture one more time. Here we go. So I'm going to use the Menelaus theorem twice, and this will also give you some idea how Menelaus theorem is actually applied in problem solving. Okay. So once I'll use in this triangle. So this is the triangle, and this is the okay, maybe I can draw it in green. This is the transversal. This red thing is the triangle, and this is the transversal. So how do I do it? Okay, so I know that AC over CQ times QR over RB times BP over PA equals to 1. Again, AC over CQ times QR over RB times BP over PA is equal to 1. That's how I remember. I just go around the triangle. Okay. All right. And then next thing is I'll use the Menelaus theorem again in here. This is the triangle APC, and this is the transversal. Okay, maybe in a different color. So here we go. All right. How do I do this? Okay, so again, I'll do AB by BP times PR by RC times CQ by QA, which is equal to 1. Right? So, okay, that's great. So we have these two. So we want this. We have these two. Right? Okay, so we're almost done. Just equate these two pieces. So this is, okay, maybe I'll just copy it. Paste it here. This is equal to, copy this. Okay. Copy this and paste it here. All right. So some of the stuff will actually cancel off. For example, okay, let's do it in a little bit different way. Let's do it like this. So we have QR by RB, right? QR by RB this is equal to, just cross multiply this stuff. So you have CQ times PA divided by AC times BP. And similarly, we have PR by RC, PR by RC. This is equal to BP times QA divided by AB times CQ. Okay, why did I take this two? Because you see, that's what I have here. I'll just cross multiply and you will be immediately able to see this. So if I just cross multiply this out, I'll have AB times AC divided by AP times AQ equals to RB times RC divided by RP times RQ, right? So on the right hand side, I have this thing, RB by RQ, right? I have RB by RQ times RC by RB. That's what I have on the right hand side, this thing. So I want this product RB by RQ times RC by RB to be equal to this, AB times AC divided by AP times AQ. So let's see, I have found two expressions. Actually, these are like the flipped ones. So I'll just multiply them. QR by RB times PR by RC equals, I'll just multiply these two. Actually, I'll copy the entire thing. Here we go. And then multiply this out. So if I do that, BP cancels off, CQ cancels off, and you see what I have is exactly what I need. PA times QA divided by AC times AB. And if you take the reciprocal, you'll get exactly this thing, right? Okay, so if you had a trouble following in some parts of the last calculation, it's a bit tedious, but you can pause the video and check again. Thank you for watching. I hope you enjoyed this video and learned something about the two main strategies that I talked about. Mathematical Olympiads are fascinating. Geometry is beautiful. I hope you are enjoying it. If you are interested in some of our programs, check the link in the description. We have outstanding programs on mathematics, physics, computer science, and statistics, and I think you will enjoy them. All right, thank you. Take care. Bye.